Hey everybody, we're live and in stereo on a Sunday morning, and the students who've joined the Sunday class and even the Saturday class, let me tell you that good days are ahead of you. These mornings are gonna pay off, and to all the Dumbo Jumbos who have registered and they don't show up to the Saturday Sunday class, I would highly recommend to watch the missed classes, watch the recording for those missed classes before joining in live in the next class, right? It's very important to watch the recordings before you sit in a live class because, again, chemistry is a story, and this story is connected so beautifully that if you miss a class and then just sit in a live class without taking the recording of the missed class, you're not gonna understand anything, right? And yes, I am sick and I am sleep deprived, but we are rolling. We love to just push ourselves to the limit. Yes, sounds good. Guys, can I start? Can I have a Gucci in the chat box? Also, I have a question. Did you guys understand everything in the last class? Was last class fun? It was a little lengthy. Today's class is going to be a little short because we are going to be done with electronic configuration today. And I'm going to teach you ways and I'm going to teach you ways that no teacher would have taught you before, and no teacher, maybe, I don't know, but a lot of teachers, they just don't know that good stuff. So I'll teach you shortcuts, all the shortcuts to writing electronic configuration and whatnot, ways that are far easier than taught in classes, and you guys will be as shocked as Reno, right? And then you guys can go on and tell all your friends about the Saturday Sunday classes, and yes, that's pretty much that. Okay, let me give you guys a quick recap. So a quick recap to what we did yesterday was that we studied about the different atomic models. Why did we study about the different atomic models, everybody? Because we wanted to figure out the electronic configuration. We wanted to figure out the idea of how electrons are distributed in shells, right? And for that, we discussed different models and their limitations. And by the way, guys, this is a part of your syllabus. You need to understand these different models. The syllabus is open in front of me and you guys can open it too. So the first model was Dalton's model. He basically just said that atoms are tiny balls, and he did not talk about the internal structure of the atom. He did not talk about the subatomic particles, the protons, electrons, and neutrons, and that was the biggest limitation, right? And we had the plum pudding model, which was Thomson's model, you know and the biggest limitation of the plum pudding model was that the J.J. Thomson thought that the positive charge is like the cake, right? It is spread, and the electrons are the raisins. That's why an atom is neutral. But we know that an atom is neutral, but we also know that the positive charge is not spread. There's something called a nucleus. So that was the biggest limitation of the plum pudding model, because the nucleus contains the protons. Yeah, and the nucleus is very dense. It's pretty small. It's very, all the positive charge is concentrated in the nucleus. It's not spread. And who figured that out? Well, my beautiful friend Rutherford, my rich fella. Rutherford performed the gold foil experiment, and he called his model the nuclear model. you know that was his model. And then he figured out that most of the atom is an empty space, and the positive charge, unlike J.J. Thomson, he said that the positive charge is not really spread, it is concentrated in a dense central nucleus, right? And then we came up with something, but he was unable to, the problem with Rutherford's experiment was it was very explanatory to much extent, but the problem was he could not explain why electrons don't spiral towards the nucleus then, right? And for that, there was this beautiful young fella, not young, they were pretty old, they were just old Dumbo Jumbos, but there was this fella, his name was Bohr. Around 1913, Bohr was the guy who actually came up with the idea of shells, right? And he mainly talked about electronic configuration. But the problem with Bohr's model was there were two major problems that proved to be wrong later on. He said that all electrons in the same shell, which is the principal quantum number, in the same shell, which is the PQN, principal quantum number, have the same energy, That's what this Dumbo said, And he also said that electrons orbit the nucleus in a circular path, right? These were the two biggest things that bit him in the bum, because after he said those two things, there was this guy, his name was Erwin Schrödinger, whose model we study in AS level now, right? So Erwin Schrödinger, okay, I'm just gonna write Erwin Schrödinger, and his model, Bohr's model was called the planetary model. Come on, I explained all of this. I'm just giving you guys a recap, right? So planetary model. And Erwin Schrödinger put these two ideas to the test, and he started to knock off electrons, and he figured out, hey, these shells, the electrons in the shells are not at the same energy level. There's something called subshells, right? So if I talk about, principal quantum number 2, there are subshells actually, the P subshell and the S subshell, right? And they have different energies. So not all the electrons are in the same energy level in a particular shell. They have subshells, which means they have different energy levels. And the way he figured that out was by knocking electrons. Done, sir. Then he realized that for the first shell, for the first principal quantum number n, if I talk about its subshell, it has only one subshell, which is the S subshell, right? So principal quantum number 2 has the S and P subshell. Principal quantum number 1 has the S subshell. And the question is, are all electrons at the same energy level in principal quantum number 1? Are all electrons at the same energy level in, not 2, I'm talking about 1. Are all electrons at the same energy level in principal quantum number 1 or principal shell 1? Yes, they are. So Bohr's idea was not incorrect in its entirety. He was right, but only for principal quantum number 1. So electrons in principal quantum number 1 are only at the same energy level because it only has one subshell, right? And then we said that the electrons are found in regions called orbitals. So subshells further have orbitals. So the S subshell has the S orbital, the P subshell has the P orbitals, and so on and so forth, right? And the D subshell has the D orbitals. So if I talk about principal quantum number 3, it's gonna have the S, the P, and the D. So these subshells are gonna have and this is gonna have the S orbital, that's gonna have the P orbitals, and that's gonna have the D orbitals. So subshells effectively are, it can either be, and if I talk about principal quantum number 1, it has the S subshell and therefore the S orbital. So realize what is, if somebody asks you tomorrow in your science class, or maybe in an interview with the Cambridge with the Cambridge University, or maybe at Imperial College London, I also give you guys so much knowledge that you guys are conceptually crystal clear and sound. So if tomorrow in an interview somebody asks you what in the hell are subshells, you can't just say, oh, in principal quantum numbers it is divided into further energy levels called subshells, right? But what exactly is a subshell? A subshell is actually either an orbital or a combination of orbitals, combination of orbitals. And the reason why I call it an orbital or a combination of orbital is because if you talk about the S subshell, it has the S orbital. So the S subshell is the S orbital, So that's why I said that a subshell can also be an orbital when it comes to the S subshell. But for the P subshell, it has 3 P orbitals. So for the P subshell, it's a combination of orbital. But for the S subshell, it's an orbital. So what is effectively a subshell? It is either an orbital or a combination of orbitals, right? And for D, it's going to have 5D orbitals. And each orbital, what in the hell is an orbital? Orbitals are basically regions in space where there is a high probability. You have to explain it to the examiner, where there's a high probability of finding an electron. finding an E, finding an electron, you know, and it only has a max of 2 electrons. It can only contain a maximum of 2 electrons. That's an orbital. Yeah, and we've discussed this in quite a lot of detail. So now, and we also know the differences, right? That if I say how many electrons are gonna be there in a p subshell, how many electrons are there in a p subshell? Well, the p subshell has 6 electrons. But what if I say how many electrons are there in the p orbital? Remember, orbital, only how much? Orbital contains how many? Only 2. Awesome. Done, sir. Dun 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 tara. Yes. Now, if I talk about, principal quantum numbers, let's just discuss them. So, if sir, is this the latest model of the atom? Yes, Iron Mike. There's no later model than the Erwin Schrodinger's quantum mechanical model. That's the latest model. Yeah, that's why you're studying it. Okay, so if you talk about the principal quantum numbers, let's talk about principal quantum number 1, principal quantum number 2, principal quantum number 3, and so on and so forth, right? Now, principal quantum number 1. How many subshells? I'm talking about subshells, right? So, how many subshells does principal quantum number 1 have? Obviously, one subshell. Which subshell? Which subshell does the principal quantum number 1, PQN1, have? Or principal quantum shell? It has the S subshell. Yeah. And because it's present in principal quantum number 1, Manur, we'll discuss this at the end, huh? We'll talk about that later. So, if you have an S subshell in principal quantum number 1, you call this subshell the 1S subshell. You just put the number, the principal quantum number before it, to figure out that this subshell, this S subshell, is present in the first principal quantum number. It pertains to the first principal quantum number. Similarly, the PQN2, I'll just call it shell. I'll just call it shell, because saying principal quantum number is just so crazy again and again. So okay, PQS, I'll say PQS. In PQS2, how many different subshells are there? How many? 2 different subshells. Which 2 different subshells? Everybody? The S and the P. And my question to you guys is, should I write a number before it? Absolutely I should. Which number should I write before this? Well, the number to which this S and P pertains. The principal quantum number to which this S and P pertains. It pertains to principal quantum number 2. So we'll have the 2S and the 2P subshell, right? Similarly, principal quantum number 3 has the S, the P, and the D subshells, right? But how do you differentiate between this and these? How do you differentiate? Well, you plug in the principal quantum number before it. So you'll say, hey, the principal quantum number 3 has SPD subshells, but it's the 3S, the 3P, and the 3D. Make sense? Yeah. And how many electrons are there in the S subshell? How many electrons? The S subshell is effectively the S orbital. Remember that. So, how many electrons? 2 electrons. How many electrons are there in the S subshell? How many electrons are there in the S subshell? 2 electrons. Yes, even if it's 2S, it's gonna have 2 electrons. How many electrons are there in the P subshell? The P subshell, not the orbital, but the subshell. It's 6 electrons. Yeah. And how many p orbitals are there? You have px, py, pz. Yes, 3 p orbitals, but I don't care about the orbitals for now. I just want to look at the subshells, right? Now, the 3s subshell, how many electrons would it have? It would accommodate 2 electrons. The 3p subshell, how many electrons would it have? It would accommodate 6 electrons. And how many electrons would the 3D subshell accommodate? 10 electrons. Yes, makes sense. Now I'm gonna quickly erase the 3D for now, because I will make you guys start filling up the electronic configuration using subshells, right? Acha, I also want to give you guys, because you guys may have different boards. Some of you guys may be for appearing in Cambridge exams. Some of you guys may be appearing in Pearson and Excel. Some of you guys may be appearing in AQA. So I'll give you all the terms for it, right? You know, this principal quantum number, it's good to have extra knowledge even. This principal quantum number was also called principal quantum shell, right? And it's also called a shelly, but it's also called something else. You can also call this the orbit, the electron orbit, depending on which board. In Cambridge, they don't use the word electron orbit, but I think in Pearson and Excel they do. I've read it somewhere in the books. In one of the books I read it, recently. So PQN, PQS, and you could also call this the electron orbit. Similarly, you can call this energy level, and you can also call this energy levels, right? You can also call subshells. You can call them subshells, and you can also call them sublevels, so depending on which board you're gonna appear in. So you can call them subshells, and you can also call them sublevels. Just a quick fun fact, right? Now, the beauty of why I made you guys write this is because I want you. Yes, what is the shape of the S orbital? Orbital looks like this, and the P orbital looks something like this, right? That's when the examiner asks you. But we're not talking about the orbitals, kiddo. We're not talking about the orbitals. We are talking about the subshells, right? Subshells have orbitals. Done. Or for S, the subshell is the orbital. Okay, makes sense. Now, why did I make you guys write this good stuff? I made you write this good stuff in order to write the electronic configuration. For example, I say, hey, sodium has 11 electrons. How are you filling it before? Well, the way I was filling it in my O-levels and IGCSE was using principal quantum numbers. Remember the O-level IGCSE electronic configuration? We used to write the principal quantum numbers. We would say, hey, the first principal quantum number would contain a max of 2 electrons. The second principal quantum number would contain a max of 8 electrons. And the third electron orbit would contain a maximum of 18 electrons. But how many do you have? You have 11, and 10 are already accommodated. So I need to just accommodate one more. Yes, that's how we used to fill it in O-levels and IGCSE. In AS level, when they ask us about the electronic configuration, they usually require the electronic configuration via the subshells. So write the subshell electronic configuration. This was the principal quantum number electronic configuration, which you used to do in O-levels and IGCSE. And now here we write the subshell electronic configuration. Now, how do we write the subshell electronic configuration? Well, you fill the subshells from the lowest energy level. So you start off with the lowest energy level and you fill upwards, right? So I'll start off with the lowest energy level, which is the 1s, and I'm going to go like so. So I'll first fill the 1s, then the 2s, then the 2p, then the 3s, then the 3p, right? Because realize, I'll give you guys an analogy for it. Think about it like this. You have to go to the 10th floor. You have to go to the 10th floor. Do you directly go to the 10th floor, or do you have to first go to the first go through the first floor, then the second, then the third, then the fourth, then the fifth, then the sixth, and then slowly and gradually go to the 10th floor, right? You don't just jump to the 10th floor, right? You have to pass through all the other floors. Even if you're going in a lift, you have to first fill up the first floor in the lift, then the second, then the third, then the fourth, then you go to the 10th, right? So firstly, you need to fill the lowest energy level subshells, and then you have to move on to higher energy level subshells, right? So first you have to fill the 1s, then the 2s, then the 2p, then the 3s, then the 3p. Make sense? Let's fill this beautiful up. And fun fact, do you know what this principle is called? This principle was called the Aufbau principle, and we'll study more about this later on. So this is basically the Aufbau principle. Oh, this looks like an I. Principle. Aufbau is, I think, is German for building up. I think it's German. I don't know. well, you guys can check it out. I think it is German, but whatever it is, it means building up. That's all I remember. So you have to build up. You have to go to the first floor, then the second, then the third, and then the second, then fill up the second one, then you have to go to the third floor. So in O levels and IGCSE, we used to write the electronic configuration in the form of principal quantum numbers, but in AS level, we write it in the form of subshell electronic configuration. Now you guys have to help me. I have to fill 11 electrons. Now, how do I fill them? Well, I'll say the first electrons, the first 2 electrons should go in the 1s subshell, right? So I'm gonna say, hey, the 1s subshell contains 2 electrons. That's why I put a square on it. I put it as the superscript. Anything below the number or a digit, that's called the subscript, and that's called the superscript. So I wrote 1, that this is the principal quantum number, that is the subshell. So this S subshell is in principal quantum number 1, and this S subshell has 2 electrons. Make sense? Now let's talk about the other one. Now I accommodated 2, I go on to the second one. So which one comes first, the 2p or the 2s? Which one has the lowest energy, 2p or 2s? 2s has the lowest energy. And the reason, okay, so why do we fill lowest energy level first? I gave you guys an analogy for it, that you have to go through the first floor, then the second, then the third, then the fourth. But if you actually want to know why, just hold up when we start studying orbital electronic configuration, electron inbox diagrams. If you want to still know, I'll tell you, it's because we want the atom to have an overall minimum energy. The atom wants to reduce its energy. It wants to have as less energy as possible. And the only way it's possible to have the lowest energy is if you fill the lowest energy levels first. Because everything wants in this universe, everyone wants to become stable. Just like Ishal, Iron, Mike Tyson, Ishal, Sikandar, Manur, all of you guys, why are you studying? Probably to achieve stability in whatever form you want, but it is to achieve stability, right? Or your parents want you to achieve stability. So realize that even atoms want to achieve. So the less energy you have, the more stable you are. Yeah, the more energy you have, the less stable you are, the more you react. So everybody wants to become stable. That's why you need to fill the lowest energy level in order to minimize, I'll write it, this is the scientific reasoning for it, in order to minimize the total energy level, the total energy of an atom. But the examiner is never going to ask you this stuff. But hey, for fun facts, fine. Okay, so first we filled the 1s subshell, then we move on to the 2s. So the 2s can contain how many electrons? 2 electrons. So I'm going to say, hey, after the 1s2, I move on to the 2s, and the 2s contained accommodated 2 electrons. Then I move on to the 2p. The 2p can have 6 electrons. 2p6. How many have I accommodated? 2, 4, 10. So I just need to accommodate one more. And I move on to the 3s. The 3s subshell can hold max of 2, and I just need to accommodate 1. And that is the subshell electronic configuration. Yeah? And then there's also a third type, which is the orbital electronic configuration. We'll look into this orbital electronic configuration later on, but for now I'll just give you a quick insight into it. So in orbital electronic configuration, I know that the 1s orbital, now I'm talking about orbitals, right? So the 1s orbital can accommodate 2 electrons. The 2s orbital can accommodate 2 electrons. The 2p orbital can accommodate 2 electrons, but that'll be the 2px orbital. The 2py orbital will accommodate 2 electrons. The 2pz orbital would accommodate, because p has 3 orbitals, so that would also accommodate max of 2 electrons. And then the 3s would accommodate 1 electron. Yeah, because you know that you have 3 p orbitals, the px, the py, and the pz. Yeah, so this is the orbital electronic configuration. Here this s means the s orbital, this p means the p orbital. Here this s means the s subshell, this p means the p subshell. For more detail for this would be later on, when we study electron inbox diagrams. अभी पढ़ेंगे, आज ही पढ़ेंगे, later on. Yeah, we're going to focus on subshell electronic configuration. Now, how do we fill subshell electronic configuration? We start with lowest energy levels. So first we fill the 1s, then the 2s, then the 2p, then 3s, then 3p. We're not going to go forward then, we're not going to go ahead right now. We're just going to fill 1s, 2s, 2p, 3s, and 3p, right? And by this I mean the subshell electronic configuration, not the orbital. Orbital later on, right? Now what I want you guys to do is, I want you guys to write the principal quantum number electronic configuration, and I want you guys to write the subshell electronic configuration for the first 18 elements. So can somebody do that? Can all of you do that? For the first 18 elements of the periodic table. The first 18 elements of the periodic table means that they'll have 18 electrons. The 18th element would have 18 electrons, right? The first 18 means that the first element is with proton number 1, therefore electron is also 1. The second is proton number 2, electrons also 2, because for atoms protons and electrons are equal. So you don't even have to look at the periodic table for this. Why? Because first 18 element means just fill electrons from 1 to 18. Yeah, come on, go for it. I'll give you guys 5 minutes to do so. I'll do a couple. So for the first element, which is probably hydrogen, the principal quantum number electronic configuration is 1. The subshell electronic configuration is 1s1. For the second one, it is 2, and this is 1s2. For the third one, principal quantum number 3, sorry, why am I writing 3? Principal quantum number 3. So the first shell can hold a maximum of 2 electrons, and the second can hold up to a maximum of 8, but it only needs to accommodate one more. But if I look at the subshell, it'll be 1s2, and then I'll move on to the 2s. That's 2s1. So can everybody do that? The fourth element, I'll write the element here. First element, second, third, fourth element. Yeah. So first shell 2, second shell a maximum of 8 electrons, but you only need to accommodate here 1s2, 2s2. Next, fifth, 2 electrons in the first one, and then 3 in the next. 1s2, 2s2, and then 2p1. Yeah, so can you guys do it like this? Should I do it, or can you guys do it on your own? Should I do it for you guys, or can you all just do it on your own? It's S, 1s, 2s, 2p, 3s, 3p. I'm not talking about D for now. खुद करना है कि मैं कर लूं. खुद करना है कि मैं कर लूं. We can do it. Okay, Iron Mike, I'm counting on you to do it. So मैं थोड़ी सी चाय पी लूंगा तब तक. I'll pause the recording. Okay, I'm gonna quickly write it with you guys, right? First, let's just write, first element has 1 electron, that's 2 electrons, 3 electrons, 4 electrons, 5 electrons, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, and 18. Okay, let's write it. So it's 2, 4 O levels, and it's 1s2, 2s2, 2p. I need to accommodate 6 in total, right? So 2, 4, and 2p2. Next, it's 2, 5, and then it's 1s2, 2s2, 2p, 3. Then 2, 6, 1s2, 2s2, 2p, 4. Then it's 2, 7, 1s2, 2s2, 2p, 5. Then it's 2, 8, it's 1s2, 2s2, 2p, 6. Then it is 2, 9. Sorry, why am I saying 2, 9? 2, 8, 1. Because the second shell can hold up to a max of 8 electrons. How do I know this? Because of the formula 2n square. So the second principal quantum number can only hold 8. Then you move on to the third principal quantum number, right? So this is 1s2, 2s2, 2p6. And see how I move on to the third principal quantum number, 3s1. Right? Then we go and we say 2a2, and then it's 1s2, 2s2, 2p6, and 3s2. 283, 1s2, 2s2, 2p6, 3s2, and 3p1. And then see, max subshell, the s subshell can only hold 2 electrons because the s subshell is the s orbital. The p subshell can hold max of 6. So after the s, I move on to the p. Then 284, 285, 286, 287, and 288. And how do I fill this? It's 1s2, 2s2, 2p6, 3s2, and that would be 3p2 now. One more electron. And then the same, but this will become 3p3. Then the same, this will become 3p4. Then the same, this will become 3p5. And then the same, this will become 3p6. Yeah. Makes sense, everybody? But now, here's the catch. Here is the problem. So you guys have written the electronic configuration in the form of subshell. That's awesome. Wow, amazing. So good. Awesome, awesome. But there's a catch now. The catch is that when you move on to the 19th element, this I call a problem. A problem for the simple mind. So let's start looking at the 19th element and the 20th element. So 19th element and 20th element are potassium and calcium. And they are going to have 19 electrons and this is going to have 20 electrons, right? Now my question to you guys is, let's start to fill it up in subshell electronic configuration. Let's start to fill it up in subshell electronic configuration, right? Now, some of you guys may think, sir, first, before we fill it up in subshell electronic configuration, let's first fill it up in your O-level electronic configuration, which is principal quantum number principal quantum number electronic configuration, right? Now, let's talk about potassium for a moment. How many electrons does it have? 19 electrons. How do you fill them? So the first shell can hold up to a maximum of 2. The second shell can hold up to a maximum of 8. The third shell can hold up to a maximum of how many? The third shell, the third shell, 2, 3 square. The third shell can hold up to a maximum of how many? 18 electrons, right? So if you've accommodated 10 here, the third shell, can it not accommodate 9 electrons? But does this look a little weird to you guys? Does this look a little weird to you guys? Did you write the electronic configuration of potassium S289 in O-levels and IGCSE? No bueno. We used to write it as S2881. Remember? We used to write it as 2881, not 289. Never. But the question is, why? Although the third principal quantum number, it can hold a maximum of 18 electrons. Why can't it accommodate the 9? It should accommodate 9 electrons, but that's not the case. We say it's 2881. That is today you're actually gonna know why it's 2881 and why is it not 289. And that is the reason why in O-levels I used to say that the first shell has 2 electrons, a capacity of 2 electrons, and then all are 8, because in O-levels and IGCSE you just needed to know till the 20th element, right? So if I talk about calcium, for calcium it should have been, keeping this idea in mind, it should have been 2, 8, 10, right? But that's not the case. It is what? It's 2, 8, 8, 2. That is what we used to write in O-levels and IGCSE. Why not 289? Why not 2810? Right? For that, you need to understand the subshell idea. So potassium, if I start filling out the electrons, I first filled the electrons in 1s, so 1s2, then 2s2, then 2p6, then 3s2, then 3p6. How am I doing this? Well, the S subshell can hold 2, the S subshell can hold 2, the P subshell can hold 6, the S subshell can hold 2, and the P can hold 6, right? So it's S, P, S, and then the 2s and the 2p, the 3s and the 3p. How many electrons are these? 2 plus 2, 4, 4 plus 6, 10, 10 plus 2, 12, 12 plus 6, 18, right? I just need to fill one more. Now, the logical thing here is to say that the last electron is going to go into 3D, right? because we know that first you fill the 1s, then all of 2, and then all of 3. You should fill all of 1, then all of 2, then all of 3. But that's not the case. Instead of the electron going into the 3d1 and becoming 289, instead of the electron going into the d subshell, you know where it goes? The electron skips the d subshell and it goes into the s subshell. So it goes into the 4s1 subshell directly. It misses out the 3d, it goes into 4s. Now the question is, why? Why does this happen? Well, the reason why it happens was the logical idea when I told you that electrons fill up the lower energy subshells first, right? They fill up lower energy subshells first to minimize the total energy of the atom. Now, you need to understand that the 4s is in fact at a lower energy level. That's so beautiful. That's an exception, right? So the 4s is at a lower energy level than the 3d. That's the reason that you need to tell the examiner. So why do you fill up the 4s instead of the 3d? Because the 4s is at a lower energy level than the 3d. Remember, always the s, not just the 4s. My question to you guys is, if I talk about the 5s and the 4d, which one would be at a lower energy level, the 5s or the 4d? Always remember that the s is always at a lower energy level than d. But in your exam, only 3d and 4s are compared. But even if I compared 5s and 4d, the s is at a lower energy level compared to the d subshell. So the 5s subshell is at a lower energy level than the 4d subshell, right? That is the reason why we used to write it as 288, and we moved on to the fourth subshell. See, the fourth principal quantum number. So this was the first principal quantum number, this was the second principal quantum number, this was the third principal quantum number, and we moved on to the fourth principal quantum number. Instead of saying 289, we don't do that. Instead of saying 289, that's wrong. We say 2, 8, and then 8, and then 1. That is what we used to write in O levels IGCSE, and this is the reason, because the 4s subshell is at a lower energy level compared to the 3d subshell, right? Now, the question is, so why doesn't... Now the question is, why? You don't need to know why. Do you want to know why the 4s is at a lower energy level than the 3d? You don't need to know it. You don't need to know it, but do you want to know? Iron Mike is saying, yes, I want to know. Samsung, yes, I want to know. Okay, for you guys. Now, whatever I'll say right now is not a part of your course, but if you know it, that's fine. You just need to tell the examiner. If he says, why is the 4s subshell filled first compared to the 3d subshell? It's filled first because it is at a lower energy level than the 3D. Now, why is it at a lower energy level than the 3D? That's not in your course, but I will still tell you. So give me a moment. The reason, oh my god, I'm so sick, man. The reason, matlab kis diwar pe sar maru. The reason why it is at a lower energy level is, I'll tell you something. The beauty of chemistry is that as you move on, as we move from one principal quantum number, from PQN to the other PQN, as I move from principal quantum number 1 to principal quantum number 2 to principal quantum number 3, right? I'm moving from principal quantum number 1 to principal quantum number 2 to principal quantum number 3, and then I'm moving on to principal quantum number 4, right? Now what happens is that the principal quantum number 1 only has the s subshell, and that's the s orbital even. Principal quantum number 2 has the s subshell and the p subshell. Principal quantum number 3 has s, p, d. Principal quantum number 4 has the s subshell, the p subshell, the d subshell, and the f subshell. Now, the beauty is that as you increase the principal quantum numbers, you also have, subshells, right? the distance of these subshells, as you move away from the nucleus, the distance between these subshells shrink. The distance between these subshells shrink, you know, as you move away from the nucleus. And if you want to visualize it, I'll even show it to you. If you want to visualize it, I'll even show it to you. I think I made it here somewhere. No, that's not it. That's it. This is the beauty stuff. I'll even show it to you. Only because you want to know. Let's erase this ganda diagram and let's look at this. Now see, as I'm moving away, this was the 1s subshell, and see the 2s and the 2p has a fair space between them, right? The 2s and the 2p subshell has quite a lot of space between them. But when I move to the principal quantum number 3, now the space is even shrinking more and more. So this S and this S had a huge space, then this S and P had smaller space. And then the space actually shrinked so much. Look at this. The 3S and the 3P and the 3D, they're so close together. And the space shrinks so much that the 4S and the 3D are actually overlapping. Literally, there's overlap in between the 4S and the 3D, and the space is so minimal now that the 4S actually, you know, enters here. It pushes the 3D outwards and it's like here. So because the space, as you move away from the nucleus, the space between subshells, the distance between subshells decreases, and there's an overlapping, a lot of overlapping, and therefore the 4S tends to have that lower energy level. So if you want the real scientific, this is not what you'll write in the exam. You'll write in the exam this stuff. But if you want to know the real reasoning is, as I move, as distance from nucleus increases, subshells distance shrink. The distance between subshells shrinks, and there's an overlap of the 4S and 3D, and 4S has a lower energy level because the overlap is in such a way that the electrons, they are bound to go to 4S first. Made sense? Happy? Made sense? Happy? Now, if I want to fill out the energy levels, so this becomes that's why we don't even use shells anymore, because it becomes so confusing to use the idea of circles. It becomes so confusing to, you know, use the idea of circles for subshells. That's why we just use these straight lines, these energy levels. So the first, the second, now let's fill the subshells, right? So we know that first we need to fill the 1S, then the 2S, then the 2P, then the 3S, then the 3P, and before the 3D, there comes this fella, which is 4S, and then you fill out the 3D. Yeah? This is the exception here. So before you fill out the 3D, you need to fill out the 4S. Why? Because 4S is at a lower energy level. Why is it at a lower energy level? Not in your course. I explained it a little, but not in your course. Made sense, everybody? Any questions? So if I were to write the electronic configuration of potassium and calcium, now the 19th and the 20th, that was the problem elements, right? So how will I write it? 1s2, 2s2, 2p6, 3s2, 3p6, and then 4s1 or 3d1. 4s1 or 3d1. Yes. 4s1 or 3d1. Yes, we need to fill out the 4s. So now the electron goes in the 4. Why? Because 4s is at a lower energy level than the 3d. Again, for calcium, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2 or 3d2. 4s2 or 3d2. 4s2, not 3d2. And that is the reason why in O-levels and IGCSE, the electronic configuration for this used to be 2, 8, 8, 1. 2, 8, 8, 2. So 2, 8, 8, 1, 2, 8, 8, 2. So should we put commas? Normally we don't put commas. Normally we don't put commas here. You can, but we don't. Yes, maza. So always remember S before D. S before D. S before D. And let me show it to you. Let me show you the beauty stuff. So let me show you the beautiful stuff. My bad, guys. See, if I show you this beauty, look at this. The 3S, the 3P, and then instead of the 3D being filled, the 4S is at a lower energy level. The 4S is filled first, and then it's 3D. And then obviously, after 4S, 3D, and then 4P. Yeah? Similarly, if I show you another diagram, if I show you another beautiful diagram, this one is far beautiful. Oh, ये तो Cambridge की book की थी, गंदी. Now, see, this is 1S, 2S, 2P, 3S, 3P, and that beautiful overlap right here. 4S before the 3D. So S before the D. 4S, then you continue with 3D, then you move on to 4P, and then you don't fill 4D, the 5S before the 4D. Right? So 5S comes first, and then comes 4D. But this part is not going to be tested. It's good that you know that S before D, but you're only going to be tested till the 4P stuff. Only here. That's the requirement of Cambridge. You won't be tested for 5S and whatnot, but remember the S before the D. The S before the D. So whenever you go out to fill 4D, remember to fill 5S before it. Whenever you go out to fill 3D, remember that you need to fill 4S before it. Yeah, I'll also show you another beautiful diagram for it. Another beautiful visualization. Because somebody told me in O-levels and IGCSE, I don't even know if you guys are sitting here, but somebody told me in O-levels and I said, your drawing is I was like, damn son, like you guys aren't even being, मेरे दिल रखने के लिए भी नहीं रख रहे. See, 1S, 2S, 2P, 3S, 3P, and S before the D. So whenever I go on to fill 3D, I need to make sure that I fill 4S. Because the 4S is at a lower energy level than the 3D. Whenever I go on to fill 4D, I need to fill the 5S before it. Would P as long come before? No. Wherever you go, it's just S before D. Okay? P's means they all follow their own trajectory. Done. This is not in your course, but before the F, you need to fill out the P, like 5P. Just like before D, 4D, you need to fill out 5S. Before the 4F, you need to fill out the P. Whenever you go on to fill the F, you make sure you fill the P. But F, MEF is not in your course. None of this is in your course. You just need to know that S would become before D. And if you want to know, P comes before the F. So whenever you go on to fill 4F, make sure you fill 5P before it. That's not in your course. The only thing that's in your course is if you go on to fill 3D, make sure you fill 4S before it. Make sense, guys? तेरी यादें वो सारी बातें. Okay, now let's start defilling it. I will give you guys all the tricks at the end, so make sure you reach the end of the class, because at the end I will show you tips and tricks to fill it. But for now, you need to know the idea, the concept. S before D, P before F. But P before F is not in your course. And when I say S before D, that does not mean that, I'm saying that fill out the 3S before the 3D. That's already filled, S before D means that when you fill out the 3D, make sure you fill out the higher principal quantum number because it's at a lower energy level. So 3D se pehle 4S. 4D se pehle 5S. 4F, that's not in your course, 4F. Yeah? 4S se pehle 5P, but not in your course. Make sense? How easy is it? Now, if I talk about sodium, It has 11 electrons. Can we write the subshell electronic configuration? Now, in A levels, whenever they ask you write the electronic configuration, they expect you to write the subshell electronic configuration, not the principal quantum number, because you've already written that in O levels and IGCSE. So subshell. So what do? First 1s2, 2s2, 2p6. See the S subshells, the P the one principal quantum number 1 subshell, the principal quantum number 2 subshells, which was S and P, and now you move on to the principal quantum number 3 subshell. Do you need to move on to the principal quantum number 3 subshell? Yes, you do. Why? Because it's 2, 2, 4, 10, and then 3s1. Yeah. Now guys, you also need to know how to defill it. Defill means, what if I say you have sodium 1 plus? How do you write the electronic configuration of sodium 1 plus? Sodium 1 plus means that you now have 10 electrons, right? But I always, listen to me very carefully. I always tell my students, don't do ternary. What students tend to do is, they say that, hey, sodium 1 plus has 10 electrons, let's just fill it out. 1s2, 2s2, 2p6, right? I never recommend this. Never, ever, ever. Because you are bound to make a mistake later on. I'll tell you what that mistake is. You never recommended this. What I recommend to students is write down the electronic configuration of sodium, which is 1s2, 2s2, 2p6, and 3s1. And then I say, now always reverse the filling. Always reverse the filling. So once you filled sodium, now I just need to remove 1 electron. So the electron is lost from the higher principal quantum number first. Remember this. So now I just put a cross here, and this is the electronic configuration of sodium 1 plus ion, right? So remember, whenever you are asked about for the ionic electronic configuration for ions, whenever you are asked the electronic configuration for ions, I always say to write down the electronic configuration for atom and then defill it. How do you defill it? How do you defill it? You are going to remove electron. You are going to remove electron from higher principal quantum number, and it's just reverse of filling. Reverse of filling. So it should always be reverse of filling, and always remove it from the higher principal quantum number first. I'm not saying the energy, I'm talking about the number. So if I say, hey, you have the 4s and it's the 3d even. Let's suppose it's 4s2 and 3d1. Where would the electron go out from? Where would the electron? Well, it's reverse of filling, but always remove it first from the higher principal quantum number. Number, not the energy number, the number. So which of these is the higher principal quantum number? Between 4s and 3d, which of these is the highest principal quantum number? Higher number is this, which is 4. Higher number is this beauty. So I'm going to remove, if I were to remove 2 electrons, I'd first remove it from the 4s, then I'm going to go to 3d. So always remove electrons from higher principal quantum number, and it's just reverse of filling. So reverse of filling and remove from high. So I filled it like this, and I'll do reverse of filling, but I'll first remove from the higher principal quantum number. The reason why I'm stressing so much on this is because what if I say write down the electronic configuration of iron 26? Iron, sorry, not iron 26, iron, right? Iron has A2 plus. First write the electronic configuration of Fe, then write the electronic configuration of Fe2 plus. Now, iron has 26 electrons. Can we fill it up? Can we fill it up? Absolutely we can. 1s2, 2s2, 2p6, 3s2, 3p6. And then, what comes first? Which one should I fill first? The S or the D? How many electrons are these? 10, 12, 18. The S or the D? The S or the D? The 4s or the 3d? So I need to fill out the 4s first, right? So 4s, 2, and then I move on to the 3d. How many should the 3d accommodate? It can accommodate 10, but how many are left? 10, 12, 18, 20, and 6 more. Yes? Is this correct, everybody? Is this correct? Absolutely it is, right? Now, this is the absolute right way of writing the electronic configuration. But your Cambridge CAIE is pretty dumb. It says, hey, I wanna club this electron. This is right, guys. By the way, Cambridge can also test this in the exam. This is right. But Cambridge says club all the subshells according to their principal quantum numbers. So Cambridge says instead of saying 1s2, 2s2, 2p6, 3s2, 3p6, instead of saying 4s2 and 3d6, you're gonna write 3d6 here and then you're gonna write 4s2 here. You're gonna club all the same principal quantum numbers together. Why does it say that? I don't know. It just, these are the two ways of writing it. Writing two ways, but remember, filling is the same. The S fills first and then the D fills. So 3p6, then 4s2, and then you fill the 3D. 3p6, 4s2, 3d6. So I used to write it like this back in the day, but Cambridge says, I've read the examination, the syllabus, it says we club I've read the examiner reports even, it says we club the principal quantum number together. So 3, 3, 3, it just looks more beautiful like this. That's what they say. But both are correct. Remember, these are the two ways of writing it, but filling both the same. First you fill out the 4s2 and then you fill out the 3d6. So first I filled out the 4s2 and then we moved on to the 3d6. First the 4s, then the 3d. Yeah? Now, if I start to remove electrons, let's suppose I'm going to start to remove electrons. Iron 2+. How do I remove electrons? Students who just write the electronic configuration of 24 electrons, they're going to get it wrong. Because what they're going to do is they're going to write 1s2, 2s2, 2p6, 3s2, 3p6, and 4s2. That's what they're going to do. That's what they're going to do. 4s2 and 3d4. That's what they're going to do. Right? If you write it directly. So I never recommend to write it directly. I would always recommend to first write down the electronic configuration and then remove 2 electrons. How do I remove, even if this is how it's written, how do I remove the 2 electrons? Where should I remove it from? From the 4s or from the 3d? From the 4s or the 3d? Remember, defilling, no Ishal. Defilling is reverse of filling. It is reverse of filling, but always keep in mind that you remove electron from the higher principal quantum number first. It's reverse of filling. You can say, sir, but you said it's reverse of filling. So I filled the 4s first, then the 3d. So shouldn't I remove it from the 3d? No, it's reverse of filling and remove it first from the higher principal quantum number. So I remove it from the 4s first. So the electronic configuration of iron 2+ is going to be 1s2, 2s2, 2p6, 3s2, 3p6, 3d6. So it's reverse of filling, but you always defill the higher principal quantum number first. Even if you filled 4s before the 3d, you might think, hey, I want to remove electrons from 3d first. No, you will remove the electron from 4s first, the higher principal quantum number, then do reverse of filling. So first these will go, then the d will go, then p, s, s, right? Like this, like so. Now, do you want to know why? Somebody thinks, sir, why? Why higher principal quantum number? Again, the why is not in your course, but you want to know, I'll tell you. If you want to know, I'll tell you. We're almost near the end of electronic configuration. Almost, inshallah. Maybe it takes one more class. That's crazy. Ek aur class, because I also have to teach you guys shortcuts. And, like teachers write, but I'll teach you great, easier shortcuts. First, I need conceptual clarity. Because shortcuts मैं सिखा दूंगा. कसम से 2 सेकंड में electronic configuration होगी. But for now, I need conceptual clarity. Do you guys want to know the reason? I'll tell you guys the reason if you want to know. If you don't, then okay, it's fine. You can just rote learn this. That always reverse of filling, but remove electron from higher principal quantum number. You can write it as a rule. Reason. Yes, reason. Okay, fine. I'll tell you the reason. And I think this was too much chemistry for now. So, inshallah, बाकी कल कर लेंगे. लेकिन I'll tell you the reason. Electron inbox diagrams वगैरह भी रहते हैं ना. I'll tell you guys the reason for it. The reason is pretty simple. See, when I was filling it, can you guys fill iron 26 for me? Can you guys fill iron in 26? So how do I fill it? 1s2, 2s2, 2p6, 3s2, 3p6, and I'm gonna first fill the 4s, so 4s2, and then I'm gonna fill the 3d. So 4s2, I'm just writing the d, I'm just clubbing the 3's together, right? So the 3d is how much? 3d? 6, I believe. 6 more are left. Okay, now when I was going to defill it, I removed electrons first from the 4s, although I filled the 3d the latest. Why did I remove the electrons from the 4s? The reason is, and that's why Cambridge clubbed it. That's the real reason why Cambridge clubbed it. The real reason is that before, when the 4s and the 3d, when they were empty, oh damn, when the 4s and the 3d, when they were empty, when the 4s and the 3d, when they were empty, which one was at a lower energy level? Which one was at a lower energy level? Which one? The 4s or the 3d? Which one was at a lower energy level? The 4s or 3d? When they were empty. S before D. So S is at a lower. Let's suppose this is the ground. This is iron. Don't put a question mark. You're saying 4s, be sure about it. If this is the ground, 1s has the lowest energy, is at the lowest energy level, 2s, then 2b, then 3s. We start filling from lowest to highest, right? That's why you fill the 4s before the 3d, because it is at a lower energy level, right? So 4s is at a lower energy level from the, it's closer to the nucleus compared to 3d. 3d has more energy, that's why it's further away. But when they are empty, since they're empty, 4s is at a lower energy level than 3d. That's good stuff. But when electrons fill in the 4s, we fill the 2 electrons in the 4s. Do you know what happens? Think about it. Use your own logic. Think about it. What in your mind would happen? What in your mind would happen for that rule to be true? That always defill it in reverse of filling, but remove it from the higher principal quantum number first. Why? Remember, we always say outer electrons are removed first. So when I fill the 4s, what does your brain say? What would happen to the 4s when you fill it? Think about it. Yes, Manur, you've got the point. After you fill the 4s, the beauty is that the 4s automatically goes to a higher energy level than the 3d. That is the reason which teachers don't teach students. They just say whenever you remove electrons, remove it reverse of filling and remove it from the higher principal quantum number first. The real reason is that once the 4s is filled, it goes somewhere here once it's filled, right? So then we know that we remove electrons, we remove the outer electrons first, and so 4s become the outer electrons. So then you remove it from the 4s, although you filled it first, but once it's filled, it will be at a higher energy level. So once you fill it, you need to remove this, then this, then this. It's only between S and D. This idea only exists between S and D and F and P, but that's not in my course. So S and D has this beautiful idea. Sir, please always give the extra reasons. They help out a lot and it's so interesting. Thank you, Ishal. I'm happy that it helps out a lot. So this is the reasoning. So you can either learn the rule, which is reverse the filling. When you want to defill it for ions, reverse filling and remove from higher principal quantum number first. No matter how you filled it, you reverse filling and remove from higher principal quantum number first, right? And the real reason is that once the 4s is filled, it basically becomes the outermost electrons because its energy increases. So you remove, electrons are removed from the outermost first. So outermost, these are gone, then this is gone, then this, then this, then this, then this. Any questions up until here, up until now? We just discussed 2 exceptions. Today, we just discussed 2 exceptions and how to do electronic configurations for ions. Reverse of filling and higher principal quantum number first. Makes sense? Any questions, guys? कोई मुश्किल था आज? पूछेगा. आसान था. To be very honest, it was easy. I haven't even taught you guys the shortcuts. पहले मैं आपका दिमाग खोलूंगा. एक दफा दिमाग खोले ना shortcuts ऐसे सिखाऊंगा. आप लोगों को कुछ सोचना भी नहीं पड़ेगा और आप ऐसे कहोगे सर इसकी इलेक्ट्रॉनिक कन्फिग्रेशन है 1s2 2s2 2p6 लाइक दिस. आई एम नॉट इवन जोकिंग. बस एक अगली क्लास का इंतजार कीजिएगा. डन गाइस. Easy peasy lemon squeezy. Any questions up until now? So today we studied how to fill the subshells, and it's not complete. It's not complete. I also have to show you guys tips and tricks. But today we learned how to fill subshells, and we also learned how to defill subshells. And the defill rule is written, but the idea behind defilling has also been projected to you guys. Any questions? कसम से ऐसी केमिस्ट्री पढ़ाऊंगा ना, खुदा की कसम सोचिएगा सिर्फ अब. अच्छा, एनी क्वेश्चंस गाइस?